All righty. So where we left off was looking at this question here where we have the reduction of this ketone with sodium borohydride, because we know that sodium borohydride can reduce a ketone, but it will not reduce an alkene. And so to draw the mechanism, we're going to draw out the borohydride ion. I'm going to leave the sodium out because it's a spectator ion. So here's our borohydride. We have our nucleophilic attack on our carbonyl. Like this, we make the alkoxide. So let's draw the alkoxide, which would look something like this. And then in the next step, we have methanol, which is going to donate the proton for the proton transfer. So we have the alkoxide grabbing the proton, and that's going to give us our secondary alcohol, which looks something like that. There you go. And you're expected to know these mechanisms, the reduction of a carbonyl group with lithium aluminum hydride or sodium borohydride. Okay, well, let's move on from there. Let's talk about diols. And a diol is nothing more than a compound that has two hydroxyl groups or two alcohol functional groups in it. And it says that diols, we name them in the same way that we name alcohols, except we drop the E, the E suffix is not dropped, and we change the suffix to diol. So let's say we have this compound here. We have a total of 1, 2, 3 carbons. We'd call this 1, 2, 3 propane diol. Or this next compound here, we would start numbering here 1, 2, 3, 4, 5, 6. You'd call this 1,5-hexane diol. So notice that you don't drop the E at the end of the alkane name. Glycol is also used to describe a compound that has two hydroxyl groups, and I'm sure that many of you have heard of ethylene glycol. It's one of the major components found in antifreeze. Ethylene glycol is. There's also propylene glycol, which is this compound. So propylene glycol is also found in antifreeze. Anyhow, so if you hear of a glycol, it's got two alcohol groups in it. It's a type of diol. Now, if you're wondering, well, how would I make a diol? You already know some ways to make diols. One way is to make it from an alkene and to do a syn dihydroxylation or an anti-dihydroxylation, but we can also use reduction to make a diol. If we take a compound like this one here, so we have 1, 2, 3, 4, 5, 6, 7. So you would call this 2,6 heptane dione is the name of this compound. It's neither here nor there at the moment, but you have two carbonyls, so two ketones in here, and so you could reduce them using hydrogenation conditions, lithium aluminum hydride conditions, or sodium borohydride. Either way, you're going to end up forming a diol. Right, so that's one way to make a diol, is from a dicarbonyl compound. But of course, way back in chapter 8, we learned how to make a diol from an alkene. So we started with something like, this is cyclohexene, and we could either treat it with MCPBA followed by aqueous acid to make a trans diol, so that proceeds via anti-dihydroxylation, or we can use a catalytic amount of osmium tetroxide and NMO as our co-oxidant to do a syn dihydroxylation. So this is review, right? This is chemistry from chapter 8, just good old chapter 8 chemistry, good old alkene chemistry. So now I want to move into section 12.6, which is a very important section. And the reason why is because we're learning a brand new reaction called the Grignard reaction. It was developed by a French chemist by the name of Victor Grignard. And he won the Nobel Prize for it in 1912. So he won the Nobel Prize a long time ago, but he won the Nobel Prize for this reaction because it was a new way to make carbon-carbon bonds, and it is still being used to this day. So let me explain the Grignard reaction to you and how we make a Grignard reagent. So it says Grignard reagents are used all the time to make alcohols. Not always, but oftentimes to make alcohols. In order to make a Grignard, what you do is you take an alkyl halide. So here we have some kind of alkyl halide, and then X. So X is usually going to be chlorine, bromine, or iodine, not fluorine. And then we treat it with magnesium metal. And if you're wondering, just make plain old magnesium metal, yes, we usually use little metal filings of magnesium. and you stir it around, and what happens is the magnesium does what's called an insertion. It sticks itself or inserts itself in between the carbon and the halogen, and that gives us a Grignard reagent. And I have two examples shown here on the bottom of the slide. The first one is taking bromobenzene. So this compound is called bromobenzene. And then we end up making this compound that's called phenylmagnesium bromide. So this would be called phenyl, right? Because when you have a benzene as an alkyl group, you call it a phenyl. So phenylmagnesium bromide. And if you want a nickname for it, people will often call it phenyl. What that is phenyl Grignard. Okay, that's a nickname for it. That's not even a common name or anything, but people use that name all the time. They'll say phenylmagnesium bromide. Oh, you mean phenyl Grignard? They know exactly what you're talking about. And the next one, we're taking 1-chloropropane or N-chloropropane. So 1-chloropropane. Treat it with magnesium. It does the insertion, and you get propyl magnesium chloride. So propyl magnesium chloride. All right, so propyl magnesium chloride is a Grignard, and phenylmagnesium bromide. These are Grignard reagents. Now, if you're looking at that and saying, well, it doesn't look that interesting to me, well, what's interesting about it is the difference in electronegativity between the carbon in the R group and the magnesium atom. So this goes way back into your Gen Chem 1 days and chapter 1 of organic chemistry when we talk about differences in electronegativity, and we say that if you have a difference in electronegativity that's between 0.5 and 1.7, it's a polar bond, but if it's greater than 1.7, it's considered to be ionic. Well, the difference in electronegativity between carbon and magnesium is only 1.2. So the delta En is equal to 1.2. And that falls under the umbrella of a polar bond, right? And that's what's being shown here. We have a dipole going towards the carbon, and that's why we have a delta minus by it and a delta plus on the magnesium. However, what we're going to do in this class, if you remember going all the way back to chapter 1 of Organic 1, I said that sometimes you can take these kind of bonds and kind of take them with a grain of salt. And sometimes we treat them as if they're ionic, even though they're technically polar. And so we can treat this bond as an ionic bond, and that is what we are going to be doing when we look at Grignard reagents. So our phenylmagnesium bromide, we're actually going to draw it like this, where I have the yellow circle. So we're going to actually draw a negative charge on the aromatic ring. And if you're wondering, well, why would I do that? The reason you want to do that is because what we're going to see is the Grignards are going to behave as very good nucleophiles. So nucleophile, negative charge, right? Nucleus lover. And they're also going to behave as strong bases. And so that's why it is relevant for us to draw Grignards with a negative charge. And if you're wondering, well, does that mean I would draw the propyl magnesium chloride like this? You draw a negative charge here and then magnesium with a positive. Yes, absolutely. That's how you would draw it. Okay. So when I draw a Grignard, I'm going to draw it with a negative charge on the carbon. So check this out. Now let's think about this. If we have a carbonyl, like a ketone, and we have a Grignard reagent, if we think of the carbon as being a nucleophile, it can do a nucleophilic attack on the carbon of the carbonyl, right? Because we have a dipole going towards the oxygen. That would give us an alkoxide. And if we could protonate that alkoxide, that means that we could convert a ketone to a tertiary alcohol. And we can do that, as you see. Notice that in the second step, we use hydronium, aqueous acid. So here's what we do. We take our R group from our Grignard reagent. Remember, it acts as a good nucleophile. It's going to attack the carbonyl carbon, and then we protonate it in the second step. Now, where it says water in the second step here, that's an artifact from an older edition of the textbook. And a lot of people complained to David Klein about that, I think. And so now, in the 4th edition, he uses H3O+. So in the second step for a Grignard reaction in your textbook, he always uses H3O+. The reason I left the water in here is because every once in a while I'll have a student who uses an old version of the textbook. And if you write water, I will accept that. However, technically it should be aqueous acid, and I'll always try to put that in my slides for you. So, I know that all of you are very astute chemists, and you're probably wondering, well, hold on. If I have a Grignard where I have a negative charge, that's also a really strong base. So, what would happen if I put that in the presence of something like water or an alcohol? And that's a good question. It says here, because the Grignard is both a strong base and a good nucleophile, you can't have any water or alcohols around your Grignard reagent. And I mean, even water in the air has to be kept away from a Grignard reagent. And if you don't understand that, we'll take a look at the equilibrium here. And I mean, there is no equilibrium, because if you take a Grignard reagent, so here's my Grignard, and you have put it in the presence of water, what's going to happen is it's going to rip the proton off of water to give you an alkane. What's the pK of an alkane? It's about 50, and the pK of water is less than 16. So the equilibrium is going to lie hard to the side of the weaker acid, the alkane, and so you've essentially destroyed your Grignard reagent completely. And therefore, it says you have to use anhydrous ethers as solvents. So the ethers that we usually use are diethyl ether, so we'll put diethyl ether, or something called THF, which is tetrahydrofuran, which is just this cyclic ether here. All right, either one of those make good solvents. So if you're wondering, didn't you tell me that we do this in the lab as undergraduates? We do the Grignard reaction sometimes. The answer is yeah, we do. And the way that we avoid having water in the reaction is that we tell our students to put their glassware in an oven to dry it for days before they get to do the experiment. So it drives all the water off of the glass. So it tries to or keeps most things really dry so that it will work relatively well. So here are some examples of Grignard reactions. Now, the way that you're going to master it is by practicing it. But here are some quick examples. Let's say we were to take cyclohexanone, this compound here, and treat it with methyl magnesium bromide or methyl Grignard. What that means is that the methyl group is going to act as a nucleophile, right? It's going to do a nucleophilic attack, and you're going to convert that ketone after protonation with water or aqueous acid to a tertiary alcohol. If we do the same thing with an aldehyde, we're going to go from an aldehyde to a primary alcohol. And remember that in the second step, you can use aqueous acid. And if you use excess with an ester, so here we have ketone, here we have aldehyde, and here we have an ester. And with an ester, it's different, because with an ester, we use excess, E for excess, E for ester, right? We use excess methyl magnesium bromide, and then in the second step, we use water or aqueous acid, and we end up with a tertiary alcohol. And so that shows you that instead of adding just one methyl group, you add two of them. And so it adds 2 times to the ester, and there's a good reason for that. All right, so with all that in mind, let's take a look at some practice problems here. And we're just going to solve a couple of these today, because I realize that I'm just introducing the subject, and you have to take a look at these to really figure it out. Well, let me just see here. It says, show how a Grignard could be used to make each of the following compounds, starting with an aldehyde or ketone starting material. Okay, so there's more than one way to make, I think everything on this slide can be made more, except for one of them, I guess. Most of the compounds on here could be made more than one way, okay? So let's just take a look at B, and then we'll move on. But in B, if you look at the alpha carbon, it's got 2 methyl groups attached to it, and then it also has a big old propyl group attached to it like this. So we could add a methyl group to it, or we could add a propyl group to it. Either one is fine, because we're making a tertiary alcohol here. That means our precursor is going to be a ketone, right? Remember, a ketone made a tertiary alcohol, and an aldehyde made a primary alcohol. So let's say we wanted to add the propyl group. Okay, we're going to add the propyl group. So if I want to add the propyl group, which is the part in blue, where I'm going to get my ketone is going to be from this part that I have in the yellow circle. So I'm going to need 1, 2, 3 carbons. Maybe I'll put those in black. I'm going to need 1, 2, 3 carbons. And so if I have a 3-carbon ketone, what's my starting material? It's the only possible ketone I can have with 3 carbons is acetone. And then in step 1, I'm going to treat it with propyl magnesium chloride. So propyl magnesium chloride. And then in the second step, I'm going to treat it with water or aqueous acid. And so that is going to give me 1, 2, 3 from my propyl group, my alpha carbon, 1, 2 methyl groups, and my hydroxyl group, like that. If you want to practice the mechanism, you could do that. You have the Grignard reagent acting as a nucleophile, and that's going to give you this compound. So you have the alkoxide like this, and then you have 1, 2, 3. And then in the next step, you're going to treat it with aqueous acid, like that. So there's my aqueous acid. This is going to pull a proton off like that, and that gives you the final product. Give me a thumbs up if you follow me, even like 65% of the way with me on that, on the rationale. And if you're looking at it going, yeah, I get it, but I'm going to have to practice it. Okay? If you're looking at it, like I've taught this class a long time, it doesn't mean I know everything, but I know a little bit. And I know enough to know that I can usually have an idea of how students react to certain things. Get it? Chemistry, reacting. Anyhow, and usually when students see this, like, oh, sugar, you know, this is pretty involved here. And it is. However, if you practice it, you will figure it out. Okay, you're not the first and won't be the last person to take it, but you do have to practice it on your own. Let's try doing it the other way. So the other way would be to add one of the methyl groups. And in that case, let me do some erasing here. If you added one of the methyl groups, then you would need, you know, all of this to make your ketone. So you'd have 1, 2, 3, 4, 5. This would be your ketone, and you would react that with methyl magnesium bromide. So methyl magnesium bromide in the first step, followed by H3O plus in the second step. And that is going to give you 1, 2, 3. There we go. And that is going to give you the product. All right. So what we'll do on Friday afternoon is we'll come back and we'll take a look at another one of these. And if there's any one in particular that anybody wants to go over, we can take some time to do that. So going back to the whole idea of an alcohol being in the presence of a Grignard, let's take a look at a compound here. Let's take a look at this neat compound. It's an alcohol. It's got a halogen on it too. Could you make a Grignard from this? Could you insert the magnesium in between the bromine and the magnesium? By the way, this is not a mechanism that I just drew. That's just an arrow for the heck of it. Technically, you know, hypothetically, it's a nice idea, but you can't do that. It's impossible. Can't do it. And if you're like, shoot, why can't I do that? Because let's think about it. If you draw it as an ionic compound, maybe I'll put the hydrogen out here, you're going to have this. Okay, so this is what I'm drawing here. Okay, that means that this negative charge can pull the proton off of here, and that will just destroy the Grignard. So this cannot be made. It's impossible to make this type of compound. And if you're like, well, what's your point, Mr. Dion? My point is this, is that an alcohol and a Grignard are incompatible. You cannot have them in the same compound. It's impossible. It's a nice idea. You're like, well, maybe if I made this, then, you know, I could do a nucleophilic attack on this, you know, ketone, and then I make a tertiary alcohol, and then I have 2 hydroxyls, and I make a diol. So the problem with that, again, is that this is going to be a side reaction, and it's going to destroy your Grignard reagent. And so what you need to do is you need to mask this functionality of the hydroxyl group. You need to cover it up some way, just like the mask on a villain in Scooby-Doo, right? You need to cover it up somehow, and then who are you really, right? You need to cover it up somehow. And the way that we cover it up is with something that we call a protecting group. And so this is your initiation into protecting groups. And we learned a few protecting groups in Chemistry 3111, but today we're going to look at just one of them. And so here's what I'm getting at, is that first, if we could take that hydroxyl group and cover it up somehow with a protecting group, then we could do our Grignard chemistry to make our tertiary alcohol. And then what if we could rip that protecting group off? Then we'd have the synthesis that we want. We would be able to do it. So, you know, your logical next step is, okay, well, what are you going to cover that alcohol up with? That's a great question. So let's take a look. In your first protecting group that you're going to learn in this class is called a silyl ether, a trimethyl silyl ether, as a matter of fact. And what we do is we take the alcohol and we convert it into a trimethyl silyl ether, right? So you know what an ether is when you have ROR, that's an ether. So if you change one of those to a silicon, then it becomes a silyl ether. So we have silicon, oxygen, R, so this is a silyl ether. Cool? And then, of course, we have 1, 2, 3 methyl groups, so trimethyl silyl ether, and we abbreviate that OTMS, trimethyl silyl. Now, if you're wondering, I'm sure this is, you're going to teach me how to make that, and the answer is absolutely I will. The way that we make it is we use trimethyl silyl chloride, this compound here. We have the acronym for it, which is TMSCl, and then we put that in ET3N. That stands for triethylamine. Okay, triethylamine. So we take the alcohol, put it in trimethyl silyl chloride and triethylamine, and that gives us our silyl ether. So silyl ether, and of course this is actually a trimethyl silyl ether, and then we end up with this triethyl ammonium chloride as a salt, and we could just wash that out of the reaction. So once we've made the silyl ether, that covers up the alcohol. Now there's a little blurb in the textbook about the mechanism of the reaction between the alcohol and the trimethyl silyl chloride. I see their point for putting it in here, but I don't know if I've ever asked a student about this. It's just, you remember that when we talked about tertiary alkyl halides, like this one I have in the blue circle, I said you can't do an SN2 on that because it's too sterically hindered. Well, when you have a trimethyl silyl chloride, you can do an SN2 on it. And if you're like, well, why can I do that? It's because silicon comes below carbon in the periodic table. Therefore, it's bigger. And since it's bigger, it leaves an opening here that it can do a nucleophilic attack and loss of leaving group. That's enough about that. I don't know if I'd ever ask a question about that. I don't even know if I ever have. Okay, but it's, good food for thought. So your next question probably is, okay, well, if I put the trimethyl silyl ether on the alcohol, how do I remove it? Good question. The way that we remove it is there's two possibilities. You can just treat it with aqueous acid, H3O+. That'll remove the whole thing. Or you can treat it with a source of fluoride ions. And if you're wondering, well, where do I get fluoride ions? From some toothpaste or something? No, that's just a joke. You would get it from this compound called TBAF. So that stands for tetrabutyl ammonium fluoride. So you have 1, 2, 3, 4 butyl groups on a nitrogen, so that's tetrabutyl ammonium, and then you have fluoride. And TBAF is just a solution in, I don't even remember, it's probably an ether or THF or something like that. You can just add it in with a syringe. It works very, very well. Very nice reagent, TBAF. So there you go, 2 ways to remove the protecting group. And like Tiana asked me earlier, well, which one would you use? Do you use this reagent or this reagent? When you give me 2 possibilities, why do you need 2? The reason is normally what an organic chemist will do is that she or he will, have a substrate and want to do a reaction. The person will try, many different reagents, as many reagents as they know on a small scale, figure out what gives them the best yield, the best percent yield, and then they'll move forward with that. All right, that's what I would do anyway. All right, so here's the overall process of protection. So we take our alcohol group, we protect it as a silyl ether. That enables us to do our Grignard chemistry, right? We first treat it with the magnesium. So that would give us OTMS, right? We have our negative charge, and then we would have our magnesium cation over here, right? And then that's going to act as a nucleophile. It can attack our ketone, and then we do a protonation. It's going to give us the tertiary alcohol, and then to remove that, we use TBAF, or you could use H3O+, and there you go. So if you're thinking this is pretty sneaky, you're right, it is, but it's a good way to do chemistry that's difficult, is using protecting groups. And if you're interested, there's many protecting groups out there in organic chemistry. We only learn a handful in this class, but there's whole textbooks devoted to protecting groups. So let's take a look at one question. I asked this question on a quiz, I think last fall or something at UCCS. So it says the following transformation involves a Grignard reaction and requires a protecting group. Identify reagents that can be used to achieve the transformation. If we look at the first compound, it has a total of 7 carbons. And then we're going to add 3 carbons, so 6, 7, 8, 9, 10. So we're ending up with 10 carbons. And you can see that we're adding these 3 carbons here. And we're also adding this oxygen. And so in terms of retrosynthesis, we have a halogen here, so we can make a Grignard from it. But what would our electrophile be? We need to react this compound with acetone. This would be our electrophile, right? But the thing is we can't just take the phenyl, aryl bromide. So we can't just take this compound and make the Grignard reagent from it. We can't do this. Okay? Why can we not do this? Why is this impossible, what I just drew? Cannot be done. Could anybody answer that for me? There's a good reason. Yeah, it's because there's an alcohol in here, right? That ruins the entire thing. So what do we have to do with the alcohol first? Anybody? Starts with P? That's right, yeah. Absolutely. You're all 100% correct. So let's delete all that junk. It won't work anyway. So let's do protection first. So we're going to protect it. And to protect it, we're going to use trimethyl chloride and triethylamine. And then we're going to make the trimethyl silyl ether. So instead of OH, we're going to have OTMS. Then we're going to have our bromine. Then we can treat it with magnesium in the first step. Then we can treat it with acetone or propanone in the next step. And I'll just draw the intermediate for the heck of no, I won't. And then that's going to give us, after protonation, it's going to give us this compound. So we end up with OTMS here, and then we have our tertiary alcohol. And then I'll just put TBAF to remove the TMS group. I've had I have in my notes here, a student asked me, well, hold on, if you're, using H3O plus, shouldn't that remove the TMS? Yeah, it probably would. It probably would. But anyhow, I'll just throw in the TBAF anyway. If a student had written, oh, I put H3O plus and that's supposed to break it, remove the silyl ether, I would accept that. Either way is totally fine. All right, give me a thumbs up. Any questions about that one? Are you going to have to study it? Absolutely. Absolutely. If you didn't, you'd be Goodwill Hunting or somebody. Anyhow, so let's move on from there. And the next section, 12.8, this deals with the preparation of phenols. I'm going to skip this section. We generally don't ask any questions about the oxidation of benzene and cumene to make phenols. The only thing that I would say that would be a wise thing to memorize from this slide is isopropyl benzene has a common name, and it's cumene. So you could call this isopropyl benzene if you wanted to, but the common name is cumene. And the only reason I tell you to memorize that is it comes up about Avogadro's number of times later on in the course. Man, oh man, he's hooked on it as a reagent. All right, so now we're in section 12.9. This is the last section I wanted to take a look at with you today. And I'll just give you a warning ahead of time. Kind of strap your skates on for this section because it's a bit of a smorgasbord of reactions. You probably noticed that the first 2 reactions on this page are both things that we saw in chapter 7. Both of these reactions come straight out of chapter 7, but there's going to be some reactions that are new in here. So something old, something new. And I'll just try to guide you through it a little bit. So I'm going to go through this kind of quickly, the stuff that you've seen before, and spend more time on the things that are new. There's a couple of mechanisms in here, just to give you a heads up, that I never ask, even though they're in the slides. I never ask my students. I just want them to understand, some little parts of the mechanism. So just follow along with me. All right, first thing, again, this goes all the way back to chapter 7. If you take a tertiary alcohol, you treat it with a strong acid like HBr. That's what's going on here. Okay, so that's this reaction here. What happens is we convert the tertiary alcohol to a tertiary alkyl halide, right? And that proceeds via an SN, zoom out here. There we go. It proceeds via an SN1, right? You remember SN1 at a time, right? It takes place stepwise. So the first step is to convert the alcohol into a good leaving group. It leaves, you make a carbocation. The nucleophile comes in and you get a tertiary alkyl halide. You can convert a primary alcohol to an alkyl halide as well. That's what's being shown here. However, it doesn't proceed via an SN1, it proceeds via an SN2. The first step is to convert the alcohol into a good leaving group, but then the bromide comes in an SN2 fashion and displaces the water to give you a primary alkyl halide. So again, tertiary alcohols, let me highlight this, converted with HX in an SN1 reaction. And for primary or secondary, it's going to go via an SN2. I don't have an example of a secondary shown on here because if you're doing a secondary, you're also going to get E2. So I'll put here E2 also in that case. But again, this is all Chapter 7 material. Where it gets new for you in this class, in Chemistry 3111, is that this reaction only works with HBr. So I'll put here works well, and I'm talking about this reaction here. Works well with HBr, not HCl. Remember, HCl is a weaker acid than HBr. And so if you want to do the same thing to make an alkyl chloride using a primary alcohol, you have to spruce up the conditions, okay? And the way you do that is by using zinc chloride, so ZnCl, okay? So we use zinc chloride with HCl, and that will spruce up the reaction enough that it will cause the chloride to be a good nucleophile and do a nucleophilic attack and form the alkyl chloride. I will not ask this mechanism. So will not ask what you see here. Will not ask. So I won't ask you about the zinc chloride acting as a Lewis acid or anything like that, okay? If you want to read about it in the textbook, I'll leave it as an FYI, but I will not ask you that specific mechanism. If you go back here, both of these mechanisms are perfectly fair game because they were covered in detail in Organic Chemistry 1. Okay, so those ones would be acceptable. All right, you guys remember the tosylate group? I know you remember the tosylate, right? If we want to convert an alcohol into a good leaving group, well, you can do a protonation, right, to convert it into an oxonium, but you can also convert it into a tosylate using tosyl chloride and pyridine. That's what's being shown right here. I think the main thing that I want you to know is that when you make a tosylate, it doesn't involve inversion of configuration, but when you do the SN2 on that, right, and SN2 always involves inversion of configuration. So inversion of configuration. So S gets converted to R gets converted to S, so on and so forth. So again, this would fall under the umbrella of, I guess this would be Chapter 7 as well. Okay, we covered this in Chapter 7, our chapter on SN2 and SN1. Okay, if you're anxious for something new, let me give you something new. These are two brand new reactions. My first office mate I had in the pharmaceutical industry, he was a huge fan of this reaction here. He loved to use it for everything. But anyhow, we do have other options to convert primary and secondary alcohols into alkyl halides. Not tertiary. So not tertiary. Tertiary, we'll cross that out. Primary and secondary. One is to use SOCl2. That's called thionyl chloride. And the Lewis structure of thionyl chloride is this. And I know you can all draw this without my help, but I'll put it in here anyway. So thionyl chloride, like that. And the other one is phosphorus tribromide. So PBr3, so phosphorus tribromide. PBr3, or as we call it in French, PBr3. Right, phosphorus tribromide. There we go. Either one of these can convert a primary alcohol to an alkyl chloride or an alkyl bromide, respectively. Now, of course, you know that PY stands for pyridine. So this is pyridine, which is just an aromatic ring with a nitrogen in it. There we go. All right. Now, before we go on to the next two slides, they show the mechanisms for both of these reactions, okay? For both of these reactions, the mechanisms are shown. I am not going to ask you the mechanisms for either of these, okay? This is going to be posted to YouTube, so you have proof that I said it. All right, so let me show you the first one. With thionyl chloride, here's the whole mechanism. And all the idea is nothing more than this. The thionyl chloride just serves as a way to convert the alcohol from a bad leaving group into a good leaving group. When it does, the chloride can come in and act as a nucleophile. And this is an SN2 reaction. Okay? That's a very quick, kind of go over of the reaction. Let's look at the reaction with phosphorus tribromide. Again, same rationale. We take a crappy leaving group, we turn it into a dandy leaving group, and then a bromide comes in and it does an SN2 reaction. What do we know about SN2 reactions? SN2 reactions always proceed with inversion of configuration. So that's what I want you to know for both of these reactions. If you have a stereocenter, it's going to be inverted from S to R or R to S. All right? You don't need to know the mechanism. You don't have to have that memorized, but you need to know that for both of these, they both involve an SN2 at the end. And when we have an SN2, we have nucleophilic attack and loss of leaving group occurring simultaneously, and thus we have an inversion of configuration. All right, so there we go. Now, next reaction comes again, just review. So from section 7.10, if you remember, this is Mr. Dion's favorite reaction. This one here is the elimination of water in acidic conditions. So if you take an alcohol, you heat the crap out of it, pardon my language, with a strong acid, it's going to give you the Zaitsev alkene. That's it, okay? So we take tert-butanol, we heat it up in acid, we drive water out of it, we make isobutylene. It's just a plain old SN1 reaction. You convert a bad leaving group into a good leaving group. Then the leaving group goes away because it's SN1 at a time. We have a proton transfer and we form our alkene. Remember though, like I told you, when you do that reaction, you usually end up with the Zaitsev alkene as being the major alkene, and you get the Hoffman alkene is going to be the minor. In fact, you usually do get a mixture, but yeah, generally speaking, you're going to get the Zaitsev as the major product. Now, if you're looking at this and saying, well, hold on, Mr. Dion, I would have done it, like, why couldn't I treat this with tosyl chloride and pyridine, right, and make the tosylate? So maybe I shouldn't have put the number 1 there. So why couldn't I do this, and make this by using T-butoxide? Could I do that? Absolutely you can. Okay, there's nothing wrong with that chemistry. I'm just saying if you're just looking to make the Zaitsev, don't worry about tosylates and unhindered bases. I would just treat it with acid. Just heat it up with acid. There we go. So again, 12.19 is just going over some of these reactions. So let's see here. Let's try. You know what? Let's skip ahead. Let's do my favorite reaction first. If I was to treat this tertiary alcohol with concentrated sulfuric acid and I heat it up, I'm going to ask you guys, where would the double bond preferentially be formed? On this bond that I'm highlighting in yellow, or this bond that I'm highlighting in green? And it is not a trick question. Where would the major product be? The double bond, the green one, or the yellow? Yeah, okay, you guys got it. Yeah, the answer is the green one, right? So I'm going to lose water, but I'm going to form this as my major product. Am I going to form some of the minor product? Sure. Yeah, probably a little bit. Right? Organic chemistry is usually not that simple. You usually cannot avoid mixtures. So this will be our minor product. So remember, major product is the Zaitsev and minor product is the Hoffman. All right. There we go. So let's back it up. Okay. I'll give you an option since I've covered most of the content that I want. What do you guys want to do? You want to call it a day and then we'll come back and tackle these, or do you want to try the first one? Yeah, let's give it a try. Okay, we'll do the first one and then we'll call it a day. All right, Maria. Well, Maria, you've got to tell us the answer for the first one then. So Maria, let's see what we're doing here. We got a secondary alcohol, and then we're converting it to a secondary alkyl bromide, and we have inversion of configuration. So this has to involve some kind of SN2 chemistry, right? Do you have any ideas for this one? I got a couple of ways to do this. Anybody have an idea? Yeah. All right, a real fan favorite. All right, so one option is to use phosphorus tribromide. Yep, that works. Or does anybody have another way of doing it, a longer way, a two-step method that you would have learned in Organic 1? How would we convert the hydroxyl into a good leaving group? All right, what if we use tosyl chloride and pyridine? We could do that, and then in the second step, we could just treat it with bromide, right? So sodium bromide. And that would do the exact same thing. Yeah, exact same thing. Now let's do one more. Let's try one more. If you wanted to convert a tertiary alcohol to a tertiary alkyl halide, this is one of the first reactions covered in 12.9. How would I do that? And this is not meant to be uber complicated reagents. It's just one thing. Not TMS. You don't need to protect anything here because there's no Greenyard chemistry. You're not changing the carbon skeleton in any way. Yeah. This one, since we're going from a tertiary to a tertiary, it would just be HBr. That's all you need is hydrobromic acid, and that's it. Oof.